Okay, so hi everyone. So welcome back to the tutorial. I'm Yunzhu Li. I'm currently an assistant professor of computer science at Columbia University. So far, what you have been hearing are some of the overviews as well as the connection between the foundation models with virtual agents and the connections of those foundation models with physical agents. So for these subsections, I'm gonna mainly be talking about robotic foundation models. So I will give an overview of what robotic foundation model is and how is it different from some of the other models, some more modularized designs you have heard previously. And I also show some of the progress over the past few years and to see how the field has been evolving over times in thinking about what type of data do we need, what type of architecture do we need, and calibrate people's expectations about the performance of robotic foundation models. So first, what is robotic foundation models? So more specifically, previously we have been discussing about these MDP formulations of different designs of these robotic systems. And if you're thinking about from this MDP formulations, a robotic foundation model is essentially a policy that map from the current either states or observation of the environment, as well as some kind of language instructions or some kind of goal specifications that provided to these agents. And this policy will map these informations into an action. And that actions will be executed in the real world to close this perception and action loop. And in talking about policies, so there are some more typical type of policies people would imagine. Example including, for example, imitation learning, in which people are learning from demonstrations. And given the demonstrations, this policy is learning this mapping from the current observational states, the mapping into the actions. Here, just one example of diffusion policy. Another categories of this type of policies, like you might be familiar with, would be reinforcement learnings, in which typically you learn the policies by interacting with the environments and accumulated the rewards, which will be used to train or somehow adjust your policies. So this, I would call them a more traditional ways of thinking about these policies, and the definitions of robotic foundation model will generalize beyond what people typically thinking about policies. Because for many of these policies, they are in general only focusing on one specific tasks, either demonstrated by humans for how to do your tasks, for example, pushing the teeth, or for specifying some specific task rewards, reorient some kind of cubes or play with the rubrics cubes. But for this robotic foundation model, it actually will not only focusing on one specific task. The real goal is still to have this policy, but generalize broadly over a range of tasks. So here I want to provide a little bit more concrete definitions. I want to draw some inspiration analogies to the so-called foundational vision and language models. For these vision language models, in general, when people see it, you realize that the outputs may not always be perfect, but will always generate something reasonable, no matter what type of instructions you give to this vision language model. And for robotic foundation model, I want to provide some similar definitions, meaning the synthesized actions may not always be the optimal actions that is used to accomplish that task, but the generated trajectories needs to be beautiful and always reasonable in solving the tasks that you give to this robot. So those is actually the foundation models that we hope to achieve with this robotic foundation models. And obviously there's so many different names for this type of models. Some people call it vision language action models, VLAs. Some people might also call it large behavior models. So depending on how you view it, but in general, they are discussing the same things. The mapping from the observation and the language instructions into some actions that is capable of solving a wide variety of tasks. So I want to because due to the time limits, there obviously has been a lot of investigations and developments in these areas, both within academia and also within the industries. And for today's tutorial, I'm mainly talking about 5 works in temporal orders. The first one would be RT1, Robot Transformer 1. It was first released in December 2022. And then it will go into Robot Transformer 2. both of which were coming from like a Google DeepMind. And we do actually see like how over time people have been thinking about things differently, especially leverage some of the foundational or common sense knowledge nerds from this large scale internet data. And then moving on, I will discuss the large scale data collections aggregation efforts to aggregate a lot of diversified set of data from, of course, the academias to collect this large scale data sets for us to get even better like generalization capabilities. Going from there, I'm gonna later talk about like open VLAs that shows this kind of like more careful designs of different modules within this vision language action models. And then like I will talk about the current state of the art like vision language action models that is like a Pi Zero, which really shows what is possible today in like achieving a diversified set of like very challenging tasks in the real environment. So I will start with Robot Transformer 1. For RT1, it was first released in December 2022. It was just like a 2 to 3 years ago, not really very far from now. And it really brings and draws inspirations from the huge success in large-scale trainings for computer visions and natural language processing. Meaning for those domains, we have seen the large-scale training by training on a large-scale data collected from internet. We can achieve this type of foundation models. It can generalize like a broadly over a wide range of vision or language-related tasks. So we're asking the questions, can these lessons also be applied in the robotic domain? And how much does those lessons apply? So then there is this large-scale data collection effort from Google's. They really spend a lot of time and a lot of money to really collect this large-scale data. Back then, like when Everyday Robotics was still there, this data was mainly like collected by Everyday Robotics. It was a whole process of 17 months with a fleet of 13 robots containing like 130K episodes and over 700 tasks. That's probably the largest data sets like back then at that times people have ever collected in the robotic domain. And given this data, you could actually realize there's a lot of questions that we could potentially be asking by given this type of data. Meaning, how well will the policy generalize across different tasks, and how like what type of data and how we should organize the data such that the nerd policy can be robust to changes in the backgrounds or distractions or variations in the environments. And also we can ask like, given this data can help us to solve maybe long horizon tasks, and can this data be used together with some other data sources such that it can achieve like even better performance. So this data, I would say, is incredibly valuable for us to answer some of those relevant questions in a large scale. So this data actually spans across like different domains. Like on the A here, that shows like what they call like the robotic classrooms that actually contains like different like copied like environments or copy like these drawers where this Everyday Robotics, this mobile robots developed by Everyday Robotics were interacting with those drawers. And on the top right, there are some kind of more mobile environments where the robots has to move around and interacting with the environments. On the bottom, it shows some of the objects they have considered in their data sets, which includes like some very like commonly encountered like daily objects, like chips or cans, etc. And based on this diversified set of data, what they do is essentially large-scale imitation learnings. Meaning the data they collected is essentially like demonstrations. It's just demonstration annotated with like a language instructions. And the demonstration contains both the current observations as well as the actions that provided by the human demonstrators. And this large-scale imitation learning is trying to learn this function and map from the current observation and the goal into the actions. And here is how the model looks like. On the left is the input, which contains the language instructions as well as a sequence of visual observations describing the movement of the robots for the past maybe few seconds. And then this information will be fed into the models in the middle, which they call Robot Transformer 1, which is essentially a combination of different like sub-modules, like film, like efficiency nets, token learner, as well as transformers. And in total, the number of parameters inside this model is 35 million parameters, which you might sound not really that much, especially compared to the existing foundation models. But even given this small amount of data, if they want to run this model locally on their computer, they can only achieve 3 Hertz when actually doing the executions in the real world. And given the generated actions, you'll be applied to the real world. Here, because they are working with a mobile manipulator, so the action space will including the actions for the base, for the arm, as well as for a different kind of modes. And then they're starting to ask questions given this type of data and given this type of models, and after they train this model, they want to start to ask some more scientific questions in understanding how we should scale and what should we expect when we scale things up. And the first question obviously is, can this RT1 learn to perform language condition tasks? Here is actually the results. Here is actually the table, the numbers show in this red box, showing the performance of their methods. You can see for sync tasks, they claim they can achieve 97% of success rates. And for unseen tasks, distractions, or backgrounds, you can see some obvious drop in terms of performance. And also on the right, you can also see from the bar plots where RT1 really achieved the state-of-the-art performance back then, especially comparing with existing robotic foundation models. And the second question is, does maybe some other data sources like simulation data help with the performance? So what they do is essentially they first train their RT1 data only using the real data shown in the first row, and they evaluate their models on objects that was never seen during the training process. And you can see the success rate was very low. It's either 23 or 7. And as they started to including simulated data in their training of this RT1, and this simulated data actually have some very nice correspondence with this so-called unseen objects in the real world. And by giving this better coverage, they actually would be able to achieve a much better success rates. Meaning there's actually 2 lessons. One lesson would be simulation data can be helpful, can be a very nice complement to the real world data. And second, even if they have spent a lot of effort, collect a very large amount of data, that is still very, very tiny pieces to what people would expect this type of robotic foundation model to perform. And it doesn't really have the good and nice coverage of those unseen objects that needs to be complemented by the simulation data. So those are the 2 important lessons to learn from these results. And the third question they're asking is about horse model generalizations, meaning would data from different robots be helpful to make the performance of this robotic foundation model better? So they consider 2 type of embodiments. The first embodiment shown on the top left, which is this mobile manipulation robots developed by Everyday Robotics, which was the platform they used mainly for their data collection. On the bottom left, which is the KUKA robots that is trying to do some bean picking tasks. They want to try to see these 2 distinct data sets, when you move them together, how will that influence the performance? And here will be their results. You can see from here, for the first row, they're actually training on both data sets. And by training on both data sets, the robots that will be tested on bean picking evaluations will actually have some very nice improvements over the baseline that was only trained on this everyday robotics data. That meaning if you include the data from some other embodiments, if that data shares some similarities with the task you want your current robot to do, that data can still be valuable. So this means the distribution of the data really matters a lot. You can see no matter whether you collect the data from the simulation or you collect the data from some other embodiments, the main goal is really to have some better coverage of what the robots might encounter in the real world. So those are some of the keys to understand about what type of generalizations you might encounter from this so-called robotic foundation models. So to summarize a little bit about this robotic transformer one, what they do is essentially large-scale language condition imitation learning. Like it just like have all the problems where imitation learning can have. For example, you just cannot be better than the experts, etc. And they really spend a lot of efforts doing this large-scale data collections, and they spend a lot of engineering efforts to do this like a fleet data collections. It's not just one robot collecting the data. So it's a fleet of robots all operated by human operators to collect this type of data. That's really like it's very costly. And this is also among some of the initial investigations to understand how we should scale up and what are some of the key questions or some of the expectations we should get from this kind of scaling up like efforts. So one of the major drawback of this work is that they haven't really leveraged this larger scale like internet data, which arguably speaking is like a multiple orders of magnitudes larger than like no matter how much data they collected. So those type of knowledge from this internet scale data hasn't been really incorporated in this kind of training process. And also because of the data size, it still cannot generalize to new skills. You can only like do some like very basic skills like pick and place or pick and pull to open some drawers. And as I mentioned earlier, like even if they tried a lot to minimize or making their model smaller, the model can still running at 3 hertz like locally. So this type of efficiency issues limits them to some reasonably simple and quasi static tasks. It cannot be really applied to some more dynamic and more complicated tasks. So this is about like RT1, which was like in 2022, but that back then it's really like inspired a lot of people like to join this directions, because at that time people already starting to see this scaling laws in some other domains, and people want to really answer the questions like, do those scaling laws also applies in robotics domain? So that leads to the second work, Robotic Transformer 2. It was like first released in July, like 2023, which is like roughly half a year later than the Robot Transformer 1. So the key questions this work aims to answer is how those VOMs, those already trained VOMs, which already shows like a hugely like and very impressive generalization capabilities, how those models can be incorporated in the development and training of these robotic foundation models. And the key ideas they propose is this so-called like co-fine-tuning process, where they will co-fine-tuning this VOM on both the robot data as well as this internet scale vision language tasks, example including like a vision question answering. This paper is also the first to introduce the name like a vision language action models, VLAs, which people now like commonly use. So in order to like incorporate it like some pre-trained or like some like a knowledge nerd in the existing vision language models, the first thing they have to do is making sure like that the input and output of those models is compatible with the input and outputs that they need for their robot transformer models. So what they essentially doing is like instead of like changing the outputs of this vision language models, what they do is to tokenize the robot actions, meaning they tokenize the robot actions to make the format of the inputs and outputs of this model to be the same. And such that you can directly use the pre-trained models from this VOM domain. And given this kind of tokenization and alignment of this robot data with this vision language data, they will start to do this kind of co-fine-tunings, in which they will have this multiple objective functions. One of the objective obviously will be training to predict the robot actions. And there will be some other objective functions to fine-tune the models to still do this kind of large-scale vision language tasks like VQAs, to making sure it doesn't forget what it has learned, but at the same time, they want to like incorporate the knowledge from the robot actions, such that like the model can also predict robot actions. And then they will deploy these kind of systems in the real world for closed loop evaluation. So there are some like key things you have to know about these models. The first one, obviously, is this kind of co-fine-tuning process. That's a key difference to distinct RT2 from RT1. And the second one is that they're now starting to have like different versions of the models. Some are larger, For example, this like a 55 billion parameters model. This is their largest models, which can run only at 1 to 3 hertz. And there are smaller models, including, for example, this 5 billion parameter models. They can run at 5 hertz. You might have the questions. For RT1, they only have 35 million parameters. They can only run their model for 3 hertz. Why suddenly like there is like other small parameters they can run like even faster? The key reason is because like they are not running the model locally. They actually develop a whole like systems that's like combines multi-GPU cloud service to run the models on the cloud. Meaning like the robots will take the observations, send those observations to the clouds, and there's some kind of multi-GPU cloud service that is actually doing the processing. So this is also like quite some efforts, but this also highlights some of the challenges of running those models like locally. And they will curate the service over the network, and that is how they can like run this type of model. It really takes a lot of effort to run RT2. So then obviously you want to ask, how well does this work? How much more beneficial, how much more improvements can we expect by incorporating these pre-trained vision language models? Here is their like results. First, like on the left, like a set of experiments. It is essentially on seeing tasks. Seeing tasks meaning the tasks that has been somehow like seen or similar tasks have been seen like during this kind of large scale demonstration collection process. You realize that the performance of RT2, which show in the green bar and the blue bars, have some comparable performance with RT1, which show in the red bar. But for some of the unseen like scenarios, especially the scenarios that requires generalizations over different type of objects, different type of backgrounds, you'll suddenly see that the RT2 will have much better performance compared with the previous like version RT1. This is really shows the benefits that's they extracted from the pre-trained like vision language model and through this kind of co-fine-tuning process. And here are just some like examples shows that what type of tasks they have been doing, which including I put strawberry into the correct bowl, pick up the bag about to fall off the tables. So this kind of model can really do some very interesting like a high level semantic reasoning of this environment and show it can like perform those tasks in the real world. At that times, there has been a lot of press coming out to like praise the achievements by Google's and almost like feel that Google have already like solved embodied intelligence. But if you're really looking closer at the results, you realize there's a lot of caveats you have to understand when you're looking at the press and the actual like robots performance. For example, here is actually one video I get from their webpage. So this is actually the first demo they show. So I'm not doing any adversarial attacks on trying to select some few bad examples. So the task is to move Volkswagen to Germany. And here the robot starting to do the task. You realize the robots actually have some very good high-level recognition capability to recognize the correct car and the correct flag. But you can just see like this low-level interaction is just not there. The robot cannot even get the pick and place right. Here's another example of move COVID to the US. Again, the high-level recognition is actually pretty good, which thanks to the development of vision language models. But if you want to generate the action all the way until the very low level, you realize the robots will just like doing some kind of random motions at the end, which doesn't really accomplish this pick and place task, which is supposed to be a simple task, to a satisfactory manner. So to summarize a little bit about the robotic transformer 2, this is really to show the power of this co-fine-tuning, which later becomes a common practice people do for training like vision language action models. It really boosts the generalizations, especially over the semantic directions and also the generalization over different visual concepts. And obviously it has limitations. It's still like limited to like a thin skill. It doesn't generalize to novel skill, but they can really show it can generate the skills to deploy them in some novel ways by combining some kind of this captured visual concepts from these VLMs. And obviously efficiency is still an issue. Like by running on the clouds, if you can still only run at 5 hertz, you obviously cannot do like a more complicated or dynamic tasks. And the absolute performance, as I showed earlier, is still like not ideal. So that means like back then, like people are very like passionate and enthusiastic about these directions. But in general, like for people who actually work in domains, we are like being like trying to be like more objective in assessing like what type of progress are we achieving and how performant those model actually is. And after RT2, this team starting to like aggregate like more data by developing this RTX. So this is really like effort that trying to aggregate all the data sets from academias. This work was first released in like October, which you realize is actually very just like 3 months after the release of RT2. And what they are trying to do is instead of just like collecting the data from a single data source, like which was the data collected by Google, they are trying to aggregate a diversified set of data sets from diversified set of sources. They in total considers more than like 22 different robots collected through the collaboration between 21 institutions. Like my lab actually was fortunate enough also to contribute data to these initiatives. And they in total demonstrating like 527 skills, which indicates like 160 like tasks. But there's also a lot of caveats around this data. You realize this data like seemingly to be very nice, but this is like a crowd-sourced data. That means the data doesn't really have very nice quality control. So it's whatever like data you have for your robots, you just like submit the data to them. This is not really a very good way to do like a quality like filtering for this data. So it does have some high quality data, but it also contains some very like bad data. Bad data meaning maybe the robot just like waving in the air, not doing anything. Like also like you could imagine, no matter how much data you have, for example, about pick and place, you won't be able to generalize to some more like complicated tasks. So meaning like a majority of the tasks shown in this data sets, I would say are more like a basic type of tasks. And obviously, after they have this data, they want to do this same like training process. And this time, like they're not just training one model, they're using the same like training recipes to training both the RT1 and also the RT2. On the left, I'm showing the inputs. The input again is the same. It's always the visual observations and the language instructions. And those information will be fed into the model. Here, this two parallel really is just like two models. The first row is what we have discussed, RT1, and the second row is like RT2, where RT1 is just large-scale imitation learning, and RT2 is just co-fine-tuning together with VLMs. And they will be deployed on the real robots. And this time, they are considering not just like one embodiment, they are considering just multiple embodiments. I think that is also a very important step forward in understanding like how this type of models can generalize to different embodiments, because the data was coming from different embodiments. So like it's natural to also ask that questions. So the questions they're asking is whether the policies trained from data from many different like robots and environments enjoy the same benefits of positive transfer. Here on the bottom is the results. So this result is interesting in a sense that it's not just results like getting by Google. They're actually getting the results by like distributing the evaluation tasks to different labs across the US. And first, like they want to see like what type of performance this baseline can have. This baseline is actually the original methods, meaning the data was actually collected through some existing work. And that existing work have their existing methods. So I want to first understanding like how will that existing methods on that tasks. So these are the numbers. And then they show like the performance of RT1, which is actually a little bit surprising to me because for some of the tasks, RT1 actually performs better than the original methods like shown by the original authors, which I think is some like positive signals here. And obviously the major lessons we should learn from this figure is that as you starting to do this kind of large scale trainings of RT1 with this OpenX datasets, which they call the model RT1X, the performance is the best. But obviously, like you can see, like the result from the auto lab, like the performance is slightly lower. I think that is highly depending on how you are actually doing the evaluations and what are the somewhat kind of protocols of doing the evaluations, which we're going to talk about later about this kind of issues in evaluation. So this is about RTX. Then like the next work is OpenVLA. So which was released in June 2024. You can see it's also like roughly half a year, like every half a year, like people trying to like release some things along these directions. And one of the major issues for this RT2 series was because those models were closed sourced, which is not surprising given that the RT2 can only be running on the clouds. So it's not something that you can very easily run in your lab. So like it doesn't really also making too much sense for them to open source their model. So people have been like starting to understanding about the practice at different components of this entire pipeline to see like if we can use better practice to make the model even more efficient and also compatible with a lab setting for people to play with. So this is OpenVLA. It's like still like very, very similar to what we have seen before. It contains this OpenVLA that was like pre-trained on some vision language models like Llama 2, Dino for like different like language heads or vision heads. They're also like trained on large scale data sets. And at that time, obviously the largest data sets will still be this OpenX embodiments. So they're actually also training on this large scale data sets. And the results are also like how to like transfer this kind of tokens back into the actions and deploy them onto the robots. So everything just very, very similar, but the devils are in the details. So there's a lot of very careful treatments in like what specific pre-training model do you use, how you tokenize your actions, and also like how you do this kind of inference, how you do this kind of code fine-tuning. So everything is actually quite an involved process. So if you want to like know more, I highly recommend you to have a detailed look at this OpenVLA. And the first author of OpenVLA also has a talk online you can check, which gives you some very detailed breaks, like a walkthrough of OpenVLAs. So like highly recommend. And they also show like this model can be deployed over a wide variety of embodiments, so not just one robot, and everything is fully open sourced, meaning they're open sourcing their codes, weights, as well as their data. So then like they essentially starting to do like two type of investigations. Like if you remember before, like RT1, RT2, RTX, what they have been always do is just evaluate the model out of the box. And so what the first thing they want to do is trying to evaluate the performance by trying to see like how good the model is out of the box. So here's the performance. So one thing you want to realize from this like figure is that OpenVLA in general achieves like the highest performance across all different kind of tasks, with one like caveat, which is like for semantic generalizations. For semantic generalizations, you realize that RT2X actually performs like slightly better than OpenVLA. And the main reason, as like described by the author, was because RT2X was using this kind of pre-trained like VLMs, and they are doing this kind of large scale like code fine-tunings. And the knowledge learned in those VLMs can be very like nicely deployed in these scenarios to handle the generalization requirements on a semantic level. Whereas their OpenVLAs were not like pre-trained on those like large scale like vision language data sets. So that's why it doesn't provide as good of a semantic generalizations as RT2X. But for other results, they show like a better performance compared to like existing methods. So I would mainly argue that the improvements in terms of the performance is attributed to like how good you can engineering like different components of the entire systems to squeeze out the performance. And the second question is that people starting to ask like, instead of just like training the model and expect the model to perform very well out of the box, can we do something more than that? And can we actually fine tune the pre-trained models to adapt to new robot setups? So now you might think like this is not like a super new, but back then like because people see like very, very significant difference by just relying on pre-training for large language models compared to add a little bit of post-trainings to your pre-trained language models. And you realize that in terms of the efficiency you are getting from this process, the post-training is actually so important and give you so much benefits than just relies on pre-training alone. So that's why people like they're starting to investigating, oh, can we actually fine-tune the models and can we squeeze out like more performance from that? And the model they are baseline they're comparing is diffusion policy. And here you can see like on the ballpark, on the average, OpenVLA actually performs the best compared to all the baselines. But here, when you look at the tasks that's only on some very narrow domain, you realize that the diffusion policies, which was directly trained on this collected demonstration, was actually performing like quite well, like sometimes even better than OpenVLAs on certain tasks. Meaning that if there's not that much of a language level generalization requirements or semantic level generalization requirements, directly collecting the data set and train the policy from scratch actually give you some like a very nice performance. But then as the task starts to become like more and more challenging, especially like when there's like multiple objects where the policy has to choose which one to pick. And this diffusion policy is starting to become like less performance compared to OpenVLA, where there's a lot of like common sense and internet scale knowledge has been embedded in the OpenVLAs, which like gives the model like a better performance compared to like diffusion policy directly trained from scratch. So also OpenVLA is fully open sourced. That you are totally welcome and feel free to play with it. It could be fun to actually like try some of the current existing models. So this is about like OpenVLA. And for the last work of these sessions, I'm going to talk about Pi0. Pi0, I would say, is the current best performing vision language action models that really gives us some like initial, like some kind of promising hope in achieving some very complicated robotic manipulation tasks. Here I'm just showing some videos, and this work was actually released quite recently. It was October last year. Here are just some kind of tasks which goes far beyond just, for example, pick and place, like pick and pull. It's starting to consider some complicated dexterous manipulations that involving like a deformable object, like close articulated object, like open the washers, as well as trying to like assemble the box shown on the top right, as well as trying to deal with some kind of ambiguities in the environment by handling like multiple objects at the same time. So this really gives the fields a lot of hope in seeing that the absolute performance of this vision language action model can actually go somewhere that's like can potentially be actually useful in the production domain. And this work was actually delivered by Physical Intelligence, which was a group of people coming out of Google. So like a lot of things just like persist into this like a new startup. So as I've been chatting with some like VCs, it's quite interesting. Like they told me like previously people have been focusing on like university spin-outs. Now they are focusing on big tech spin-outs, meaning they are using these research institutions in those like big technology firms to de-risk some of those technologies. And then they spin out a team to do a startup. And they are very happy to fund this type of startup. So these are just some of the initial results delivered by Physical Intelligence. So again, the high-level framework is, I would say, nearly the same compared to what we have seen before. In general, it's just a large-scale data sets. Of course, a lot of different embodiments. So they have been using like data from different sources. Essentially, you have three sources. The first one is OpenX. Is like the RTX I showed earlier. But they have been reasonably selective in like what subset of data from OpenX they want to include in their pre-training procedures. Like this, like I said earlier, like not all data are of equal value. Some data are just more interesting than some other data. So through these aggregations, they will actually develop this practice of identifying like which data might be more interesting. So they include those data in this pre-training phase. So that is data from RTX. They also have the data from the internet, and they also collect their own like large scale, like a Pi course embodiments, like a robot data. And given this course embodiments data, they are starting to do this kind of pre-training, like I mentioned, also combined with internet scale data as well as RTX. And this type of pre-training is also like just the same as I have showed earlier, this kind of co-fine tuning with different objectives, etc. And given this model, they can already achieve some like a reasonable zero shots performance on in-distribution task shown on the top right. And obviously, they can also start to do post-trainings, as has also been a practice I mentioned earlier, drawing from the natural language processing domain, those like language-related foundation models. And by using this post-training, they can achieve more complicated tasks. So more specifically, they consider simple in-domain data. That's simple in-domain tasks. They can be reasonably accomplished with their like a pre-trained model in a zero-shot fashion. And by like fine-tuning, like doing this kind of post-trainings with like newly collected demonstrations, you'll be able to do one more complicated in-distribution tasks, like for example, like folding shirts, or for some kind of like unseen tasks. And they have also been open sourcing like their stuff, which is very nice. Like and I have colleagues who have already, their labs has already been like deploying this OpenPy, and I actually received some like reasonably good like feedback from them in like what type of zero-shot performance you might actually get. So like if you are interested, you are highly recommended to try their codes and checkpoints they released online. So those has been like general overviews about the developments of this so-called robotic foundation models or vision language action model or large behavior models, depending on how you call it. Like we have really seen a lot of some interesting like progress over the past few years. And those past few years, you're actually seeing the progress in how people treat different aspects of this recipe differently. For example, data, people originally starts with just their own collected data, and then they shifted to aggregate data from the internet and also aggregate data from some like other academic labs. And later they realized maybe some data of not of the equal values. So they started to collect the data again, but they're still also leveraging the internet data. So those type of like iterations of what type of data is the most useful has become some kind of like interesting but hard to concretize lessons. Sometimes I will ask their team members, okay, what do you consider to be like an interesting data for pre-training? Sometimes their answers would be actually be very vague in a sense that, oh, as long as the robot is doing something interesting, it's probably okay. As long as the robot is not like a static or sitting there doing nothing, those data can potentially be useful. But you probably also need like a very high quality like demonstration data for your post-trainings. So there actually will be different considerations when you collect the data for the pre-training and also for the post-training. And on the model domains, at the very beginning, people trying to like do this kind of end-to-end imitation learning. Now people starting thinking about how you can do the code fine-tunings with some other objectives to making sure this model also preserves some knowledge like already embedded inside the existing vision language models, like very powerful vision language models. And for the downstream deployments, people starting from like a single embodiments now move on to more and more diverse and multimodal like embodiments. So those type of like evolutions over time is actually quite fascinating to see. And I'm personally super excited to see what's coming next. So this actually wraps up my session on robotic foundation models. Any questions? So I can answer your questions from like different perspectives. The first perspective is about the coverage for the pre-trainings. So for example, like we now have very powerful like large language models, but we still don't have equally powerful visual foundation models. They can solve all the vision tasks at the same level as how GPT can solve natural language processing tasks. This is probably because we don't have enough data, probably because we don't have the right training recipe. But the fact is that we don't have this kind of like a ultra, like a Oracle visual foundation model that can solve all the vision tasks. And I would like to argue this robotic tasks is strictly more challenging than vision related tasks. So, and we do not really have that much data actually on the robots. So this is a domain where in order to have the right coverage for the type of tasks you want the robot to generalize, it's extremely challenging, both in terms of the cost it involved to collect the data, but also involves like what type of data do you collect, what type of coverage do you get, and what type of like performance like you want to achieve. Meaning you want to have this kind of ultra coverage for all the tasks you want to have, it's going to be very, very hard. So that's why people are starting to use this type of post-trainings. And for post-training, it's actually like a bit nuanced how to actually do this type of post-trainings. Because for post-trainings, they typically require this data to be very, very high quality. High quality means the trajectory has to be very clean and very smooth. You do not want the robot to have a lot of like zigzag motions or like some kind of random pauses in the middle. You want a continuous, smooth, and maybe shortest like path to actually accomplish that task. And for this type of like trajectories, you don't need that much, but the caveats maybe like still maybe hundreds, if not thousands of trajectories for this type of post-training. And then because the data is just so clean, it doesn't involve too many recovery behaviors. So they actually expect the data used for pre-training contains those kind of recovery behaviors. So combine this recovery behavior from the pre-training and this clean trajectory from the post-training, that actually gives you the best performance. So then, like, what type of behavior do you have? What type of recovery behavior do you have in your pre-training becomes a lot matters. Meaning, depending on the distribution of the data used for pre-trainings, the type of like benefits you could expect for the post-training stage can be very different. For example, for close folding, they actually collect a lot of recovery behaviors during this pre-training phase, so they can do the close folding very nicely. But for many other tasks where they do not have those kind of coverage from their pre-training stage, they actually do not have as much benefits for some other tasks. I hope that answers the questions. Thank you. Any other questions? Okay, if not, okay. Mm-hmm. So I actually have one slide later when I'm talking about challenges about this figure AI. But figure AI, their result, I would say, is quite impressive in a sense. I think that's some of the first results showing like two humanoid robots like interacting with each other, collaborating with each others. And there are some very interesting designs in like their overall like model structures where they have this kind of system 1, system 2 type of combinations of the different modules. But like without like more information, it's really hard to understand like how much progress they actually made. Meaning like, yes, they can show demos, but have they ever done like proper evaluations of the results? It's actually a question. I will later tell you like evaluation right now is actually a challenge. You cannot take just one demos very literally. There's a lot of nuances to like this demo, and obviously like the demo they show is in a very, very clean environment and very constrained environments where the robot doesn't really move that much. So I would actually, so what I mean is that the result is not surprising. It's just a very impressive engineering effort that puts things together. That's how I would characterize like my impression of their progress. Okay, so I will move on to the final parts of today's tutorial, which is about the remaining challenges. Okay, so talking about remaining challenges, I will now starting to talking about, because I've been talking about robotic foundation models, I'm just starting to talk about the evaluations of the robotic foundation model. It actually becomes such a huge bottleneck and for us to make concrete progress in this direction. So first, like if you read carefully into the papers, you realize the results are not consistent with each other, like over time. For example, here are the actual results reported from RT1 paper. Here's how they say their performance is. Remember, 97% of success rates. And we're starting to talking about like the results reported by RT2 paper, like because RT1 was a baseline. You realize that this performance actually drops quite a lot compared to what they reported in their first paper. And then later from OpenVLA, the performance of RT1X, which is supposed to be a more powerful versions of RT1, actually the performance also drops quite a lot. So I wouldn't blame them because like the evaluation is very hard. They probably are using like different tasks, different initial configurations, different lighting conditions, different like setups of robots, like different set of objects. So there are a lot of variables in this kind of like a space that actually makes some like a concrete statements about how much progress you are making becomes extremely hard. So it's actually a very, very noisy directions. Sometimes I'll be very hesitant in entering these directions because of the issues with evaluations. This is both noisy and costly, as has been evidenced from the results reported by them. So currently, the evaluation is primarily conducted in the real world. And here I'm just showing like one paper from Aloha, one figure from Aloha that shows like this kind of Aloha setup currently at Google. So they have a grid of Aloha that trying for them to do some evaluations about the performance of different types of models. And This process is, again, costly and noisy, meaning if you were to do the evaluation or I am to do the evaluations, the results can be totally different from each other, depending on how we specify the initial configurations. The lighting condition can change. The policy runs in the morning the result can be very different from the policy running in the afternoons. And as you're running the policy for like 1 hour straight, the robot will become like heated, and the result can also difference depending on like how long you are into this kind of evaluation process. And because they are using Aloha, which if you know is actually not a very, very good robots. So there is actually inter-robots inconsistencies, meaning the policy running on this robots, the results can also be different from the policy running on the other robots. So there's a lot of variations in here that actually is really, really hard to come up with some very concrete like statistics to understanding the progress. And I was chatting with friends at Google DeepMind. Their exact words was, we have large enough budget such that we can still make progress. This was their exact words, meaning like the evaluation is so costly. Like for example, if you are working on deep learning, you probably will think, oh, we have like hundreds, if not thousands of checkpoints. I want to do evaluation every day. But in reality is that at Google, even at Google, where they claim they have sufficient budgets, they can still only do a handful, definitely like maybe more than 10, definitely not over 20 like evaluations every day. And they still have to wait maybe for 2 days for the results to come back to understanding like the performance of their current checkpoints. And if you have been training like imitation learning models, for example, like diffusion policy, ACT, etc., you realize there is very, very weak, nearly zero correlations between the training loss and the real world success rates. Like meaning like even if you see the loss plateaus, if you train the policy for longer, and highly likely actually the performance, the success rates will become higher in the real world. And this is because like the metrics between the objective for the training and the task specific metrics, they can be different from each other. For example, different policies, you are predicting the noise, but in the real world evaluations, the task success definitions are actually like specified by humans, like more subjective manners. In the training, we'll only consider certain like a time horizon, where during the testing, you are rolling for much longer horizon than during training. So it's a lot of nuances in actually doing like a proper evaluations of this like robot learning models in the real world. So then you probably want to ask, like, why don't you do the evaluations in simulations? So there actually have been works in this domain that has been using simulation to do the evaluation, example including Simpler. And there has also been a lot of people in the AI, in more general AI fields, they're trying to tell robotics people like how to actually do evaluations. Example including for them behaviors or habitats, where people have been bringing the knowledge and the lessons they learned from, for them, computer vision communities, and trying to come up with this type of benchmark to make concrete measurements of the progress in the robotics or embodied AI domain. And this is actually a very good like thinking. For example, the reason why ImageNet was successful is because ImageNet has been the like a metric to measure the progress of deep learning and computer vision, at least for a few years. But we currently do not have this type of things in the robotic domain. So people want to build that. But that doesn't take long for people to realize, like even if they put a lot of efforts, so there are still a lot of like gaps for them to provide like concrete measurements of the progress. Like example would including like symmetry real gap, because like people are dealing with rigid object, deformable object, closed, articulated objects. Currently, we do not really have a simulator that can simulate everything around us to a fidelity that is satisfying for this kind of evaluation purpose. And obviously, you want to do actually efficient asset generations if you want to do like a evaluation using simulation. And sometimes in robotics, you realize buying object from Amazon is just so much easier than trying to create a simulatable assets. And I was actually involved in this behavior like projects. Back then, we have an army of students and trying to label the assets, like label their mass, these physical properties, articulations, which actually is quite painful. And also, obviously, it's not just about the objects. You want to also generate this environment to digitalize the environments where the robots will operate in. And you probably will also do procedural generations of a diversified set of plausible environments where the robots might encounter when they are like operating in the real world. And in which you probably want to capture some statistics where the apple is more likely to be in the living rooms or in the kitchen than, for example, in the restrooms. So those type of nuanced statistics in creating this type of a distribution of evaluation scenarios has been also quite tricky. And obviously, people still haven't been really have a concrete answer for the correlation between the simulation and the real world, meaning how much lessons we learned in doing evaluation simulation generalized or transfers to the real world to guide us to do better developments of these robot learning systems. So we are really calling for the ImageNet for embodied AI. So that would actually be the first challenge we are encountering right now for this robotic foundation model, which is evaluation. And then, we have been talking about, for example, this foundation policies. And actually, the other sides of the coin is actually the foundational world models. So my definition of world model, of course, a lot of people have their own definition of world models. People call A, B, C, D, F, G, all of them world models. And my definition for the sake of today's tutorial is action condition future prediction. So meaning it has to consider different initial configurations, has to consider different input actions. As long as it can predict the future as changed by the input actions, I will call it world models. And if you're thinking about what does it take to train this so-called foundation robotic policies, it's actually this action conditions robot interaction data. But in order to train these foundational world models, what you need is also this action condition robot interaction data. So this is actually come as a so-called free lunch, where they actually can be this kind of data, same data, can be used for different purposes. If they all have been used just to train a policy, I would argue it's such a waste for all the knowledge and all the information that's embedded inside the this type of data. And the model is essentially a forward process, and the policy is actually an inverse process. Whereas the model tells you how the future will look like given the current state and action. And the policy essentially is that I will have the future I want to achieve. What action should I take? So this actually is a forward and inverse. It's actually the two sides of the same coin. So they actually can be very nicely integrated together and reinforce each other's. And I see some very promising directions of trying to build this foundational world model and to see how they can help us develop better robotic policies. And there are some existing series of work, including this world models developed by David Ha, as well as, for example, some other works like Daydreamer that has a sequence series of Dreamer series. And there has also been works recently from for example 1X Robotics. They are releasing their data and trying to generate this kind of world model challenges. And recently from NVIDIA, they're also releasing this Cosmos and trying to show you can actually learn this kind of action condition video prediction models, which can act as a world model either for evaluation purpose or either for data generation purpose. So, but obviously there's a lot of considerations along building this kind of world models. First question would be, do you want 3D? Is 3D important? Now people doing a 2D, a pixel image-based predictions, and do we want to add a little bit of 3D, such as the whole model will become more structured and possibly more sample efficient and more generalizable? And what type of structural pride can we add? Can maybe there's some kind of physics-informed designs in the whole process that give you just so much better modeling of this kind of physical interaction process in the real world. And obviously, given this type of model, this kind of nerd model, previously I was talking about physics-based simulators, behavior, habitats. Now I'm talking about this nerd simulator, which is the neural simulators. We still have to answer the questions. How does the data generated by this neural simulator correlate with the real world? That's for either evaluation or data generation purposes. And then going slightly back to some of the things you heard earlier today about developing this foundation model for embodied agents. We have a lot of different kind of so-called foundational models, some language related models or vision related models. We have already here how they can be used in coherence, but modularized designs to enable the robot to do tasks that was not possible with more classic robotic agents tools. But current foundation models are not tailored for embodied agents. I believe Manning have also shown some failure cases of existing foundation models in terms of their reasonings about embodied related tasks, where the current foundation model have very limited understanding about geometry, embodied, and physical interactions. So we're asking the questions. Existing foundation models are trained using RL from human feedback, but can we also allow the model to do RL from embodied feedback? Can the interactions with the environment, the agent's interaction with the environment, the data generated from these interactions to help us develop better foundation models to allow the model to have the right levels of understanding about the physical interactions with the environment? And the next, I believe, is also very, very important. If you have some more rigorous and more comprehensive understanding to make more concrete claims about the performance of your models, which can only be achieved by like quantifying the uncertainties to develop our belief, our confidence about our systems. For example, this is a framework shown earlier by Jia Yuan, which contains like different modules throughout this entire systems. And there's like different modules that can actually be replaced by foundation models. And we want to like properly like assess and measure what type of uncertainties can we get and how like confident we are about the outputs from the existing foundation models. And want to understand how those measured uncertainties can be or should be propagated throughout this kind of entire process. And those uncertainties how can those uncertainties be properly handled by our planner or controller design, such that we can compensate for those type of uncertainties. And then as a whole, how can we verify the overall robustness of the framework to like making more rigorous claims about the performance of this model? That's the only way like we can build confidence about these models when they're actually working around us, working like around our kids and in our like a human environments. And obviously down the road, like for the robot to like work in diversified set of environments, this adaptation and lifelong learning also is super important. For example, like we want the robot to be able to adapt to different scenarios. It's okay for the robot to overfit to your home and then like overfit to my homes. But still, for the robots to first deliver to your home, it has to like adapt to your environments. Not just to your environments, but also adapt to your preference. Where do you want your like socks to be? How do you want your like table to be set up? So there's a lot of like a preference and environment specific things we have to like develop in order for this model to be really useful. And then as we humans have been constantly improving our like interaction skills through the interactions with the environments, we also want our robots to also improve through their experiences. Meaning after the post-training, maybe the performance is still not 100%. What we do then? Probably there could be some kind of combination between imitation learning and reinforcement learning that allows us to like further improve the model's performance for that specific task. And the next point is about some practical considerations of foundation models. Because I have been working on robotics for a number of years, I have very hands-on understanding about every robotics work is essentially a system work. For a robot to work in the real world, it is essentially a system. You have to handle and consider all different kind of practical constraints and practical considerations by moving all different kind of components together for the robot to actually make physical interactions with the environments. And there's a lot of considerations like delays, what type of computing, do you do the computing locally or do you do the computing on the GPU, on the TPU, like clouds, in the clouds, and how different kind of modules can work and talk to each other. Some modules might be very good at handling the high level queries. Some modules might be very good at solving some kind of low level like interaction tasks. Like, for example, like earlier, like I believe Wenlong showed this works poster and recap. I was also author of the both works. Like Wenlong really spent a lot of efforts putting like different modules together, because like different modules, they might run at different frame rates. Different modules may have their advantages, limitations. Some modules work in these scenarios and some modules may be better at some other scenarios. How they can be nicely combined together really requires some kind of system level thinking and system level like development. As I have also been mentioning like earlier, for this very recent examples from Figure AI, there are so-called Helix like engines. They are also combining both this kind of high level 7 billion pre-trained VLMs and this 80 million like transformers, respectively as system 2 like reasoning about the task and the environments, and system 1 that generates like a high frequency, high frame rate actions that can be executed in the real world. So meaning different modules might be good at different things, but if you want them to work very nicely with each other, system level design and system level considerations is extremely important. So at last, I want to conclude today's tutorial But I really like talk to you about our hope for this tutorial, that we want people to work on the virtual agents and physical agents to talk to each other. So like over the past many years, there has been a group of people working on like virtual agents, another group of people working on physical agents. They're not like the communication between them, I would say, is quite sparse. Like the problem domain and the specific like tasks and specific design considerations about their modules are also quite different from each other. And recently, because of the obviously development of robotics and development of those foundation models, people are starting to have more and more conversations with each other. It's also the goal of today's tutorials. We want to show to you how foundation models when interact with embodied agents. This embodied agents contains both virtual agents and also the physical agents, and how we can have the more structured way of thinking and unifying both camps, unifying both the virtual agent people and physical agent people by all framing the problems under this kind of MDP framework, like a Markov decision process. And we have been discussing a lot of key techniques, emerging opportunities, and also notable challenges as I have just discussed. So I want to conclude today's tutorial here, and thank you all for coming, and I'm also happy to take any more questions.
You mentioned that there are several projects that are also foundation work really higher. And I really feel like parents for the CLA, and I don't see an easy way to incorporate that often. Do you think they are valuable? And do you think
Actually, I see a very concrete way of how to use these so-called word models for the robot foundation models. The reason be that if you think about the word model, let's say first let's define the word models. Word models essentially is a predictive model that taking the current state and action predict the next states. And it can be both instantiated as a physics-based simulator, can also be instantiated as some neural simulators. They are operating on different state space, and they are also governed by different mechanisms in the middle. Like one is physics, another one will be some kind of neural networks. So, but they are all future prediction models. And then you are thinking about what's the inputs of the existing policies. Like I have already showed many times, the inputs to the existing policies are just the language instructions and also the visual observations. We can easily handle the language instruction parts, but as long as this so-called word model can generate the desired or close enough visual observations that is indicative of what the robots might encounter in the real world, that can be this very nice interface to bridge between these word models and robot foundation models. We have already seen existing works actually that do more realistic renderings from physics-based simulators, and to show the correlation between the policy's performance in the simulation and the real worlds. A concrete work will be the simpler, because for this kind of neural models, a lot of work is actually about action condition video prediction. So if you have your video prediction, you naturally have this visual observations that can be inputs to your policies. And also recently, people have been also developing 3D action condition video prediction models. And by moving on to the 3D space, there are also so many different tools from the computer vision communities on how to do proper renderings, like neural radiance field, Gaussian splatting. They are all very handy tools of giving you a very nice visual observations, visual renderings that can be inputs to your robotic foundation models. So to answer your question, I actually see a lot of different ways of combining these word models and robot foundation models. So if I understand your question correctly, your question is essentially about, for this type of kind of predictive power, should we just use them as some kind of standalone module that interfacing with this VOA, or should that actually be some kind of integral part of this VOA? I think both can work. I think both are valid way of thinking about how they can be used together. For example, the existing VOA starting from RT2, they start to do this co-fine tuning of fine tuning the robot's action predictions and the prediction of the answers for some visual question answerings. You can also add some kind of supervisions here, like also to predict the future. So I think like predict the effects of their like actions and trying to see if their predicted outcomes matches what they actually get from this real world. It also nicely like matches what we discussed earlier about this reinforcement learning from embodied feedback. So I think there's some very nice like ways of combining those two, and all of them can potentially be very promising. So I'm personally very excited to see like what's going to happen in the coming years.